Hello, I am Byungmin Kim from IIXR Lab, presenting a seminar on the paper Physics-Aware Hand-Object Interaction Denoising, published at CVPR. To begin, let me briefly introduce hand-object interaction reconstruction. Achieving accurate and physically plausible hand-object interaction denoising is a challenging task. Firstly, the resulting hand pose must be realistically feasible. Excessive bending due to joint angles or unrealistic stretching of a deformable hand due to joint position should be avoided. Additionally, because the hand has a high degree of freedom, achieving a desired pose can be difficult. Secondly, we need to learn the spatial relationship between the hand and the object. The spatial relationship refers to the relative position, angle, and distance between the hand and the object, essentially representing how and where the hand interacts with the object. Ultimately, this is akin to capturing the user's intent, making it a difficult task to represent and learn this interaction from data. Lastly, it is necessary to learn not only the spatial relationship, but also the physical interaction between the hand and the object. Various forces are applied to the object depending on the hand's pose. A force acting perpendicular to the object may create pressure, while a force applied horizontally could result in friction. Depending on these forces, the object may move within the hand, remain fixed, or even slip away. Accurate simulation requires precise tracking and the ability to capture these forces, making this a complex and meticulous task. If the hand-object interaction motion sequence were an exact replica of reality, it would be challenging but not impossible to solve. However, due to the limitations of tracking technology and motion capture, we inevitably obtain noisy motion sequences, which necessitates hand-object interaction denoising technology. This technology aims to process noisy input with interpenetration issues or unstable grasps, producing a denoised output that resembles a realistic grasp. Next, I will introduce the essential knowledge needed to understand the target paper, beginning with the autoencoder. An autoencoder is a neural network that extracts and compresses the key features of input data through an encoder, then reconstructs it into the original form through a decoder. The compressed result is referred to as a feature or latent vector. Because the autoencoder compresses and reconstructs key data characteristics, it is effective for denoising noisy data as we have here. The next concept is PointNet. PointNet is a deep learning model designed to directly use unordered point clouds as input for effective classification. Virtual objects consist of numerous vertices and edges densely connected. Representing this as a single dataset is complex, and data size becomes very large. In the field of hand-object interaction denoising, the hand and object are thus represented as point clouds. However, using unordered point clouds with existing technology is nearly impossible. Techniques like CNNs are highly order dependent, whereas point clouds lack a specific order since vertices have no inherent priority and object data vary in size, making traditional architectures like CNNs difficult to use. PointNet extracts features from unordered data by learning each point individually using MLPs, which can handle point clouds because they learn independently of neighboring points, unlike CNNs. Additionally, PointNet uses a symmetric function, max pooling, which is unaffected by order. In max pooling, which is only the maximum value of sampled points is used for compression, meaning that even if the order changes, the result remains consistent. This enables PointNet to extract features from unordered point clouds effectively. Now, what are the advantages of combining autoencoder and PointNet? First, point clouds, represented as a collection of fine 3D points, capture the complex shapes and positions of both the hand and object accurately. Second, PointNet can learn the structure and relationships in hand-object interaction without being order dependent. Third, the autoencoder can compress complex hand-object interactions while retaining key features. Lastly, the autoencoder can denoise data by effectively learning features even from noisy data. This makes it highly suitable for hand-object interaction denoising. One notable paper that utilized these technologies is TOC. TOC is a model that takes incorrect 3D hand-object interaction sequences with interpenetration or non-contact problems and outputs refined motion. TOC's main contribution is capturing continuous spatial-temporal interactions. To represent continuous spatial-temporal interactions, TOC devised the TOC field, which is object-centric and assigned to each point in the object's point cloud. The TOC field consists of a binary flag indicating contact status, the sign distance to the closest hand point, and the coordinates of the closest hand point. These values vary over time and contain spatial information, enabling the detection of spatial-temporal changes. Next, an autoencoder with PointNet is used to remove noise from the input. Since the autoencoder alone cannot capture temporal information, additional processing is required. The paper employs a GRU, gated recurrent unit, which stores essential information from previous frames and discards unnecessary details, enabling the processing of the temporal information in a motion sequence. This paper places greater emphasis on the encoder, so I will skip the details of the decoder. The target paper uses autoencoder, PointNet, and TOC field as discussed. Although TOC performed denoising of hand-object interaction sequences by considering spatial-temporal correspondence, it did not account for physical elements. This paper enables physically aware hand-object interaction denoising by using torque field data and key points representing joint positions. Additionally, data and physics priors are learned through two-stage training. First, training stage 1 uses ground truth motion data for training. Noise is randomly added to the ground truth motion, which serves as the input. Specifically, key points representing each joint position and the torque field are input into the autoencoder. This yields latent space set through PointNet and an RNN. When the output is decoded back into key points and torque field, the same process is applied to the ground truth motion sequence, resulting in differences due to noise. This difference can then be used for backpropagation, enabling the model to output data similar to the ground truth even when noisy motion is input. After the training 1 ends, the autoencoder is frozen and a new mapping layer pi is created to learn the physics prior. Positioned between the encoder and decoder, it is trained using GCL, grasp credibility loss, and MFL, manipulation feasibility loss. GCL is a loss function that adjusts the hand pose in each frame to conform to the object's shape, preventing penetration. MFL maintains realistic hand-object contact along the object's overall movement path. In more detail, GCL introduces the concept of penetration depth to prevent penetration. For example, suppose the noisy input shows penetration into the object compared to the ground truth. If there is a 0.01 on the object surface corresponding to point H1 on the hand, and noise moves H1 into a new position, penetration depth is calculated by the dot product of red vector and the object surface normal vector N01 at point 01. This results in a value less than 0. If the finger is lifted, the value becomes positive. This absolute value increases with deeper penetration or greater distance from the object. MFL comprises force error and manipulation expense. FE prevents unnatural force application. For instance, if the current force applied at point 01 is small f and the required force is large F, the magnitude of the difference factor is summed. Smaller differences yield lower loss values, approximating the required force. ME ensures that force is applied only at contact points. Assuming the contact threshold is C contact, if the distance between the nearest hand point and an object point in one frame is D, then D minus C contact will be negative if there is penetration and positive if the finger is not in contact. As force should not be applied outside contact points, loss increases in such cases guiding the model to apply force only when the finger is within a certain distance from the object. In summary, GCL prevents penetration, while MFL ensures stable object grasps without interpenetration or detachment, ultimately producing physically plausible motions. Once these two training stages are complete, feeding an actual noisy hand-object interaction sequence as input is a refined sequence that prevents penetration and is physically plausible. This is visually demonstrated in the results. The paper compares TOC's performance on the 3D dataset, graph, and the 2D image and depth dataset, whole 3D. The target paper shows a clear improvement in preventing penetration while preserving the hand's general shape in noisy input. This also holds for whole 3D, with the input image of the hand grasping an object. Both raw tracking and TOC exhibited penetration, while the target paper effectively prevented it. The paper also conducted quantitative comparisons. MPJPE and MPVPE represent the differences in hand joint and vertex positions between the refined data and ground truth data. IV is the volume of penetration. PD is the sum of penetration distances, and contact IOU compares contact maps. If the distance from the object surface from the hand is within 2 millimeters, it is considered a contact point, and a contact map is generated for comparison. Plausible rate indicates success if PD is below 1.5 centimeters and force error is below 0.1. This result measures various noise motions generated by the paper. T represents noise in the overall hand position. Theta represents noise in hand joint angles, and global orientation noise was applied to all noise motions. No changes were applied to the object's orientation and position except for global orientation adjustments, likely because altering the object's shape changes the grasping motion itself. In conclusion, I have summarized the contribution and limitations. This paper developed an interaction denoising model robust to noise using limited data such as key points and TOC field. Furthermore, it achieved physically plausible motion through physics-aware laws, preventing penetration. However, the model requires high-quality ground truth data, meaning that results may vary greatly depending on this quality. Although the paper notes this limitation when discussing prior research, as the model is not fully autoregressive, some limitations may still persist. This is the end of the seminar. Thank you for your attention.